We are in the physical chemistry class. We have unreachable goal of predicting and interpreting instrumental measurements. And currently, we are looking on the particle in the box and trying to make connections to real life. Last time we got new skill, new theory, new methodology of so-called density of states, which is needed to treat situations when amount of eigenstates is very large and when they're sparse, when they're not sparse but dense, right? And our main tool was the Strowman, who was walking forward and looking backward. So the main method in what we were doing was to count number of states as function of energy and then taking derivative of it, right? And then by this derivative of number of states is density of states, and it is a way to describe a system when number of states is high, when states are dense. Oh, now I focused on both Adam and Sibyl. Last meetings, it was not possible to catch everyone in the camera. So what should we do right now? The exercises that we were doing were focused on one-dimensional model. When we neglected, we took X, or maybe we took Z and X, neglected X and Y. It would be reasonable to look on all three dimensions, or at least one more and then another. And then if we would have unlimited time for this class, if it would be 1 year class, we probably would draw orbitals and slowly but surely go through all details. And now we need to speed up and go to most important thing. And most important thing is the density of states, like energies of eigenstates, if we have more than one dimension. The summary of today's outcome, the summary of today's lab, and the summary of the homework that you hopefully submit by Monday will be that same as a technique of spectroscopy that you answered during the interview on Monday. By an analogy with spectroscopy, the density of states of a box of different dimensionality can tell us which box we have. So density of states is one-dimensional continuous figure, and by looking on this image, you will be able to recognize what was the dimensionality of the structure. Is it reasonable? Yep. Okay. So let's see. Oh, hello, Alison. Hello, my. Let's see, which slides do we have? Oh, now it is ready to share screen. So although I am going to jump over eigenfunctions for three-dimensional box, this is typically included in basic textbooks. And the best way I can recommend to look on it is about 1 hour from the beginning of the doctoral defense of Dr. Aaron Fordy, who did it here at NDSU at summer, and I'm advertising him because he is graduate from my group. So when it was time for him to answer questions, he was appealing to the concept of the particle in the box to explain and provide background for the results which he did with more advanced methods. And here is the image which would illustrate and would serve as a complementary image to our today's meeting. So if instead of one dimension we have three, if box is three-dimensional, it is confined, it is infinity everywhere outside of the box for all three dimensions. The eigenstates will be again signs, but those will be signs along x, y, and z, and overall function will be product of them. And if one wants to plot, originally we used to have like half period sign, then full period sign, then 3 halves along one dimension. Here this image shows, you see this little cube, right? And the lowest state is a product of 3 half period signs. So along each of the dimensions, it gets to 0 when it approaches the edge. And therefore it forms a shape that looks like a sphere approximately, but it's a product of 3 signs in x, y, and z. Then next 3 states, which may have the equal energy if the size, if the box is truly cubic, will be full period sign along either z direction. Now it is 1 nodal point and 2 maxima along z, and still signs along x and y. Alternatively, one can have this sign along y direction, and along others it will be half period, or along x direction. And it's interesting that it looks already similar to hydrogen atom, right? S and p orbitals, but there is no atom, there is no hydrogen. It's just a box, 3-dimensional box. But you see that there will be some universal features that one can expect in other systems. And the energies, so instead of 1 quantum number, one does have 3, right? For lowest state, their values are 1, 1, 1. And as far as we go to higher energy, either one of them gets 2, and then one can expand more and more numbers. If you are planning to take a statistical part of the physical chemistry and thermodynamics in the next semester, it will be language of your exercises for the whole semester. You will be selecting quantum numbers, identifying energies, and then plugging them into Boltzmann distribution to see what is the probability to such state to be observed. So eigenstates and eigenenergies will be very similar to what we had, so quantum number squared, but since there are 3 of them, there will be square of each of them, right? So the density of states is here with different width parameter, and basically this one is illustration. It's not a part of the lecture at all. I just thought that it could be satisfying your curiosity, but our main goal for today would be to focus only on equations for energy as function of quantum numbers for 1-dimensional, 2-dimensional, and 3-dimensional box, and see how the density of states will depend on this dimensionality and on the size of the box. If it deviates from cubic, or if it is like looks like a box for ski, pizza box, or cubic box. Okay. One part of entertainment is done. So 2- and 3-dimensional books. Here is a plan for our lab tonight and for the homework which is due on Monday. So you see here is a LX, LY, LZ, which is size of the box. And basically we will play changing these numbers, running this code and see what happens. I plan to give detailed comments on this next homework on Friday and Monday, so that you get some suggestions. And we are on the green point in this space of methods. So I'm going to attract your attention and show a movie. So you will see a three-dimensional box with certain size, and then the density of states. During the class time, we will derive such density of states by pen and paper. And last time we already did it for a case of long, quite of a one-dimensional thing. At the lab tonight, we will basically run similar code and fabricate density of states as a function of the size of the box. And here is a summary of this exercise. I'll first try to go and stop a couple of times and then run it fully. So if we expand the box, states become less dense, more dense, right? But they look like individual peaks. If we keep increasing, we see that more states kind of climbing down from higher energy to lower energy and condense at lower energy area. And as we go further, it looks like seal, Bermuda seal on the seal ship, right? The 1 over square root of energy. It is offset and it started at a certain point, but you see the shapes that you have derived on Monday. Now, so and it becomes more continuous. So one doesn't see signatures of individual states, and it looks more like a continuous mathematical function. Now, if we grow, and then we start to expand this box for ski or whatever, quasi one-dimensional box, if we try to increase it in y direction. You see this seals for the ship try to perform the same trend. They climb down. And these seals are spaced more dense. And they add together to each other. And probably they will create another shape. Let's see what happens. So they're almost indistinguishable, but it is hard to say what is a shape. But let's wait a little more when it looks more like a box. So which shape would you identify on this image? How would you call it? Just try to give some name. I don't know, you are on the camera. What do you see?
I see a rectangular prism, kind of like a flat box.
Well, the pin is a box, and what is on the bottom?
That is the number of states, right?
Density of states, but how is there an object in regular life that looks the same way?
Oh, like stairs.
Yeah, exactly. So I think we are. Thank you, Adam. We are on the same page. So would you agree that it looks like steps on stairs? So in two-dimensional box, when a particle can equally go into one and another direction, it is expected to be like stairs. So flat range and then another flat range. Okay, so what would happen if you go further? Stop. Here. Yeah. So if we go past this point And now we are going to grow the box in the Z direction. So we can expect that same as before, these shapes will start climbing down and become more dense. And it will be like ascending stairs to infinity. But question is whether the length of this and height of the stairs will stay the same or it will be modified. So would you say the stairs are equally different? Are they becoming shorter or longer as we go to higher energy? So overall shape will be like ascending with smaller and smaller slope, right? Check how it goes. So at some point, the individual steps will be indistinguishable. And indeed, it goes as ascending line with slope becoming smaller and smaller, right? So for large size three-dimensional box, it goes this way. And then it goes down, but it is not a fault of a theory. It's a fault of the computer code that all computer codes have range of applicability. And this code is not applicable for energy bigger than some threshold. But our goal for today is to prove by pen and paper these shapes. Linear seal for both the steps or continuous, just one density of states, it does not depend on the energy. And then the ascending shape with where the slope becomes smaller. Okay, so this image is an answer to your homework. So basically what you're expected to submit by Monday is this image generated by yourself. So try to generate it yourself, submit it and provide little explanation how you, as you did last time, what do you see and how you interpret it. So for individual states, it's this way. For one-dimensional, it's seal shape. For two-dimensional, it is stairs with flat surface. And for three-dimensional, it's ascending. Whew. Basically, we are done. Fun part is done. Now we are going to the boring part. So I cannot tolerate my own handwriting. It's ugly, but please tolerate as a payback for entertainment at the beginning. So if you have the red font corresponds to one-dimensional box, blue stuff correspond to two-dimensional. If you have second dimension, we have a sign pi n pi over L, and here it should be multiplied by y. Yes, and we do have another quantum number n sub y. The energies of in two-dimensional box will be controlled by these two quantum numbers, nx and y, both squared, and we should divide by the size of the box. In case the box is not square, these numbers will be different for each of them. So it's just here we assume that motion of an electron in each of direction is independent from motion in another one. Mathematically, it's quite an approximation. And we skip justification. We just assume it is this way. And then motion can have different regime of confinement in x and y dimension. So basically, we are going to practice this equation: find number of states as function of energy, make derivative over energy, and find density of states. Our answer should be flat line, constant. So let me take a little interview. High school. Sibyl, I'm going to ask you first question and second to the Nate. So what is the area inside a circle?
The area inside of circle basically is the A is the function there PR squared.
PR squared.
Yeah.
So radius of circle
Circle
squared.
Yeah.
Yeah, thank you. Nate, what is the volume of a sphere, of the space inside the sphere?
I know it's up there, 4/3 pi r cubed.
So it's a third power of the size.
Yeah.
Okay, so if it is a rectangular cube, it is just size cubed. If it is, but if it is a spherical shape, it is some factors like 4/3 pi, but still the third power of, because volume is measured in length cubed, right? Okay, we will appeal to this basic heritage from high school today, so that if you ever need to serve as instructors, you can justify and tell like there was a reason to study well in high school. Okay. So I'm going to employ our old friend Strowman. And remember, last time it was walking in one-dimensional space. Now we do have a three-dimensional space. And no, I'm too quick. Two-dimensional space. So Strowman, and last time it was walking forward from the origin to the area that corresponds to higher energy. Now, if you have two-dimensional space of quantum numbers, and x and y, what would be the trajectory for our Strowman to travel? How would you suggest any ideas how we can, which orders should we give to a Strowman?
You should travel in like an arc shape.
Okay, arc shape is one option. Anything else?
Linear.
Linear. Okay, linear in which direction?
In the negative direction.
Where should he start?
Probably at like the top of the graph, like 6 or so.
Okay. Okay. So yeah, thank you, Joe. So let's keep.
Can you repeat the question?
I will. I'll check if I can pause recording and tell an anecdote, because I don't resume recording. I don't know if it is appropriate for academic stuff. So if we are thinking in terms of like human or Strowman or a point traveling on some trajectory in some area, we need to identify a trajectory. When it was one-dimensional linear motion, there were no options. Motion can be on either forward or backward. But if it is a two-dimensional space, there are many options for trajectory. So how could the Strowman walk? So you want to give it like angular trajectory.
Yeah, I could go down and then
Down and up. Okay, so it was down. Nate suggested to go on arc, and then suggested go from top to the bottom. Then Lola suggested to go down and then to the right. Okay. Adam was already given an interview. Let's ask Wyatt.
He's starting from the top, right?
I will not say yes or no because the intrigue would disappear.
He could travel in a diagonal line.
Perfect. Enough. Enough for the interview. It's really good. So let me talk about it a little bit more. I realize that this question needs to be asked after many years. It was looking evident that we need to go from, last time we were going from minimal energy for minimal quantum number to maximal. And now you have suggested go from top to the bottom, go to the arc, or go down to the right, and then going on the diagonal. Basically, the Strowman should be our cartographer. He should cover all space. But if you want to make connection to density of states, maybe we want to maximally repeat our previous experience and send him to go from the origin, and then just like a dog to explore and go in maybe this way to cover all space, or maybe we want him to go on a straight line on a diagonal, but always look back. So what would be the assignment? What will be the lab notebook? What does this Strowman needs to record? What was the Strowman recording last time? Huh? Yeah, what is behind him? And basically, he was telling how many states have energy less than his own energy at current position, right? So now I am out of ideas how to make it entertaining, but the energy will be an x squared plus ny squared. So when a Strowman at a certain point, the energy of all, so these little circles are eigenstates labeled by two quantum numbers. So all quantum states which will have the same arc length from the center will have the same energy as a Strowman at this point of trajectory, right? And all states behind, all states inside this quadrant of a circle will have energy less than he has at a certain point. So I don't know how to answer my own question, whether he should go as arcs or on the diagonal, but he should look back and count all circles inside this blue border. Make sense? I'm happy we agree on this. So a little example. So if you are staying on this purple point, then an x squared plus ny squared will be 9 plus 16, 25, because it's like a point for 3 and 4, right? And if you take square root, the radius will be 5, or radius square will be 25. So we need to find all points with radius less than 25. And assignment for the Strowman will be to count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? When he moves to the next step, it will increase by 13 plus 1, 2, 3, 4. Next will be 17. So it's good. We can even design a little exercise of pretending that we all are strong people and counting this, but it's too silly. We can do it by pen and paper in a more elegant way. So the energy is energy of minimal state, and Lola suggested last time to change it from 0 to 1. It will be more correct to put here E11 of energy of this state. I'm just a little no time to change it. But minimal energy multiplied by this nx plus ny. Would it satisfy you? So the energy is proportional some constant time nx squared and y squared. Okay. Then if we divide energy of a state divided by this dimension constant, then we will have a radius, but not in our Cartesian space of distances, but radius in this energy space, or energy radius in the space of eigenstates. So we will put the bar r squared. Make sense? So we need to count all little circles that have radius from distance from the origin smaller than this one. Now, if we do, oh, by the way, here is the graphical interpretation some of you may like. So area here is number of states, number of circles in the thin layer is density of states. How density of states depends on how far we go from the origin. So we can immediately tell what is number of states based on your high school equations. As soon as we got equation for the radius, we can use pi r squared, as Sibyl taught us. But since it is not a full circle but quadrant, we divide it by 4, right? So number of states is 1/4 pi r squared. Now we have nothing to do other than making. So here is this one is I'm repeating some equations. Energy as function of quantum numbers. Now energy as function of radius, radius as function of energy, and here is the number of states as function of radius first and energy second. If one cancels all constants, then it will be energy and size of the box. So you see, it is energy in which power? First, right? What is the derivative of x? What is the derivative of independent variable in the first power? 1. You're done with 50% of the class material. So it will be constant, what we've got when we run our computer program. So density of states for two-dimensional state will be 1 or 1 multiplied by constant. Examples: graphene, molybdenum disulfide, the bismuth telluride, the network of metals and non-metal in a flat panel. Here is the lead halide. So there is a class of two-dimensional materials. Even there are journals of two-dimensional materials, and most of them obey this law to have density of states flat. If there are exceptions, they need to be explained separately. So based on the help from Joe, derivative of energy over energy will be constant. So you see there are flat regions, right? And these little jumps occur because of the change of the quantum number in the other direction, which is still there. If you absolutely neglect z direction, it will be flat everywhere. If we do computer simulation as we will do tonight in the lab, there will be these little steps from other dimensions. 14 minutes. Okay, Strowman, working in 3 dimensions. We do have the same image with 3 quantum numbers in x, y, and z dimensions, right? And we need the Strowman to walk from the center to the surface of this universe, from the core of the planet to its surface or whatever, and count amount of quantum states behind him, under the surface. Nate told us that it will be proportional to the cube of the radius, right? So 4/3 pi r cube. So we need to express radius as function of quantum numbers, which will be like an x squared and y squared and z squared and then square root, right? Okay. So if the energy is defined in the same way as in the particle of the box, and I remember one of the class attendees was telling that this equation is not possible to memorize. I agree. I memorize it only 5 minutes before the class and then forget. But what can we identify in this equation, which would be great if you memorize, but since I'm not memorizing myself, I cannot request it. So we do have several segments. We have segment of constants, which we can forget for time. We have a segment for size of the box, and we have segment of quantum numbers, right? So the quantum numbers are squared and added together, the size in the denominator, and then there are constants. So this quantum number squared can be interpreted as distance, right? And then we can invert, like keep r squared here, multiply left and right by L squared, and divide by this constant, right? And then take square root. Then we will have this energy multiplied by all the stuff L squared and this constants here. And then on the left, we will have the radius. Make sense? Okay. And this radius can be plugged into 4/3 pi r cubed, right? Which we will need to divide by 8 because it is octant. We chop the space for the because all quantum numbers are positive. Okay. So we can express number of states as a formula for the volume, and the radius is in the power 3, right? But originally, the radius on our previous slide, I'm going to flip back, energy was in the power square root, power 1/2. So if I am super lazy and if I don't care about constants, the only thing I should worry about is the power of the independent variable. So the radius is energy to the power 1/2, and then it comes to the power 3. Right? So to the answer for number of states will be, we can combine all constants in this C bar, and then the energy will be into the power 3/2, right? Okay. And if we need to find density of states, it will be just derivative of the power 3/2. So derivative means subtracting 1 from the power. So it will be, and power goes also is assigned to the constant. And then energy to the power 1/2 is the square root of energy. Everyone is convinced? Okay, yeah, thank you. It looks like not very complicated, right? But there was a Louis Bruce Nobel Prize in chemistry for just identifying these relations in respect to nanostructures made of semiconductors. So it's just a different glance on things. So here is the square root line. Here is what one can get from the simulation that we will focus on during the lab. And here is the summary, I would say. I don't know what else to say. Just if the box is very small, the confinement is so strong that it pushes all states away from the ground state. Lowest state will be just one line, and here it will be a superposition of few minor states, but spectrum will look very much like atom. And at the very beginning of our meeting, you saw that even orbitals look like in hydrogen atom. But if we increase the size of the box in one dimension, it gets the shape of the main seal. If you increase in 2 dimensions, it becomes constant as function of energy. And if you make just big box in the limit of if the size of the box approaches infinity, then we will have our 3-dimensional electron in the free space. So this should be quite universal. So density of states grows as a square root of energy. Experimentally, there are, I think I did mention it last time. So electrochemistry and scanning tunneling microscopy directly measure density of states, and you put a sample, you make measurement, you get the figure on your computer that is being measured, and you can say, oh, it looks like today we are having a 2-dimensional object on our plate. So it's possible to recognize some features of the system if it is small and invisible, but you get some characteristics, you can learn about system from density of states. In the subject of computational chemistry, it's one of the simplest and primary ways to characterize any material. So if you take model of a molecule, you first think you compute density of states, because it's a universal feature that can be compared between different objects, and with a large or small number of states, one can put it on the same figure and analyze. There is a little thing which you can close ears and do not hear. Some 2-dimensional objects do not have flat density of states, and the simplest of them is immediately this example. So graphene has different shape of density of states because it has non-standard momentum dispersion. So do not catch me if you read some literature and you see deviation of density of states from the flat. There are exceptions, but those which we explore today are quite universal. Okay. Done. I think we are done even earlier. So thank you for your patience. I'll stay here to answer any questions, but meeting is dismissed. If you are online, you are welcome to disconnect. If you are in class, you are free to adjourn, depart. And if you have some questions, just stay a minute, I'll answer. My